if you've had a chance to skim the book, there's actually about a 5-paragraph section on mobile IP. And I would suggest you read that because it's very interesting to see, here you have this paper, which is a lot of pages, right? And here's what these guys thought it really distilled out to. And they also have they also bash it. So you might be interested in seeing why they bashed it. One other thing I just wanted to check. How well did you guys get this whole thing about the flow control for congestion? I felt like I went through it maybe a little bit too fast. And I'm willing to go through another example so that you guys understand what, this window, like why you pick a certain window size. Do you guys want that? Okay. There are actually, if you go to the internet, there are resources that you can find that tell you how to tune these parameters. Like they say, if you're they say that if you have a Windows 98 or 95 machine, the default parameters that are set for these windows tend to be oriented towards modem users. So when you plug in something like high-speed access at home, you might not actually get the performance that you're expecting, not because it isn't available on the internet on the link, but because these parameters are set the wrong way. And unfortunately, there's no easy way to click and say, now switch me over. I don't know about Windows Me if they take that into account. But definitely, if you have a Windows machine, 98 or 95, there's a guy named Joe Navas, N-A-V-A-S, and he has a great FAQ about optimizing your internet connections. And I get into that stuff, so it's fun stuff. Okay, so the problem here was in flow control was you have in the default case, the simple case. Sorry, Louis. Yes. Oh, it fell. Thank you. In the, you remember we had the sender, we had the receiver. If we send the datagram and then wait for an ACK, this is a lockstep protocol. And the amount of time it's going to take to send a number of datagrams is going to be equal to that number of datagrams times the average round trip time. And what we want to do is actually lower that number so that we can send more data in less amount of time. So the way that's done is using windowing, in which case you send a set of requests, in this case 4. And the point is that you send the next one without waiting for the ACK that comes back. Okay. Now, at the end, let's assume that this ACK here, the last ACK that comes back, is going to be something that tells you, OK, you can send the next window from the receiver. So then what we have is the amount of time it takes to send n-1 of these times just from the sender side plus the last round trip. Okay, so that's how you do windowing. And the question is, how do you decide how many of these datagrams to put into a particular window? Now, I gave you this equation yesterday, which was window size equals round trip time times what? The bottleneck. How fast the bottleneck can process these. So I think the easiest way to do this is to let's take a very concrete example and let's see how things, what happens when you use this as the window size, what happens when you try to push the window size up, and what happens if you try to pull the window size down. So let's say you have, now I'm going to simplify this. Let's say you have a network where the latency is, I'm just going to use seconds. Usually it's in milliseconds, but let's say it's seconds. 3 seconds one way, 3 seconds the other way. And let's say that the bottleneck here is that your receiver can process these at 1 datagram per 6 seconds. So according to this equation, what should our window size be? 1. Okay. So this is a lot like lockstep, right? So let's see what happens in the lock step. Well, we're sending, and let's see what happens when we try to push it above that. So let's say the sender sends 1. It takes 3 seconds to get there. Okay, so we're now at time equals 3. We have something here. Now we immediately can immediately send an ACK back at that point. So at time t equals 6, right? What's going on? Well, this guy is halfway through processing that packet, right? This guy's already, or that datagram, which is the message. Over here, this guy's got the ACK back now that says, go ahead and send me another one. And so you start sending another one. Now what happens 3 seconds later? Well, this guy's done, and he gets the next one. Okay, so notice how this guy's always going to be getting a packet right when he's finished with the last one. Okay, what happens if we send, let's say we send 2 instead of 1? Well, we send 2. Now, by the time we start sending the next 2, this guy's going to be done with, by the time he receives the next 2, he's going to be done with the first one, and he's going to have one that's buffered that he's going to start working on, right? But all of a sudden, like, these other 2 show up. So now he's got to have a buffer that's at least of size 2, so because he's going to be working on the one that he had buffered that he had just gotten to. Now, what's going to happen to that? What size buffer do you need in this case in order to handle that window size of 2? Is it bounded?
No, it keeps increasing.
Keeps increasing, right? Because now the work is going to keep increasing, right? So eventually, you're going to have congestion, which in this case, eventually, once they run out of memory, or something's going to break, and you're going to have to drop it on the floor. Your buffer is going to overflow. Okay, so one works, 2 doesn't. If you think about this, even 1.1 will cause you will require a buffer size that's not fixed. What about less than this? If you send less than, I mean, then you're under optimizing, right? So if this is the highest rate you can go, then pick that one. But let's just to make it even more clear. Let's see what happens when you switch this to processing 1 datagram every 3 seconds. Okay. So what's our window size now? 2. Okay. So what happens here? You get 2 messages. This thing gets 2. So it's got 1 buffered, and it's processing 1. And this is at t equals 3, right? Now, it's going to send the ACKs back as it's doing that, right? So at t equals 6, this guy's going to put 2 more on the line, and what's going to happen? This one is going to be done already, right? Because it's 3 seconds. T equals 6. It does 1 datagram every 3 seconds, so it's going to start working on the buffered one. So it's processing 1. 2 on the way. Now what happens at t equals 9? It's done processing that one, and it gets the next 2. Excellent. So notice that we're using the network here as a weird way to store messages. Right? It's almost like as the message is going, it's being stored by the network. And that's the buffer. That's in essence acting as a buffer as an extra buffer for this receiver, right? Because the message is here, it's processing, and then when it's ready, it's just a buffer that happens to have some time constraints, because things are gonna arrive when they do, and you don't get a choice whether to slow them down. Now, if we try to increase the window size, what's going to happen? Well, let's say we do 3, right? It's the same as before, right? You're going to have to start buffering these things, and then soon you need more and more buffer space as you get more and more packets coming through. Now let's take one last one, which is, let's say you can do 3 datagrams per second. Okay, how many are we going to be sending now?
18.
18. 18 at once. Boom. You send 18 over. So what's going to happen there? You send 18 over. So now this guy's going to have time t equals 3 is going to have 18. And that means he's going to start processing 3. And 6 of them are going to be buffered. At time t equals 6, I'm sorry, can't add today. Subtract. At time t equals 6, the sender is going to get an ACK back saying, I got all 18. And what's going to happen here? Well, these are going to be done. So we're going to have another 3 processing. I'm sorry. Thank you. I was like, wait a minute, this isn't going to work. This is too many. So, okay, let's see. This is 3 processing. Oh, okay, so this is 3 at 3 times 3. Yeah. Right. So each second. So it's going to be done. It's going to have done another 3, another 3, another 3. Right. So it's going to be done with how many at this point? 9. So it's going to have 9 buffered. And it's going to start processing, these in the next 3 seconds. It's going to process another 3, another. And guess what? By the time that's done, and it gets the next 18, it's all going to be these 9 are going to be done because we had 3 seconds and we do 3 per second. Yes.
Quick question on the S side. Once it gets the ACK, what happens?
Once he gets the ACK, he says, okay, the receiver's got acknowledged this. So this is this case. It gets the ACK. Now this ACK is, I'm assuming that it's an implicit permission to send more. So he's going to say, oh, I've got the ACK. Bundled in with that is a message telling me I can send more. So I'm going to send the next window.
So wouldn't that take time?
It'll take a little bit of time. In this case, I'm assuming that time is negligible compared to the seconds. But that could be, when you compute the round trip time, usually if you do it empirically, you send a ping back and forth and you take some average. That's going to include the amount of time that this computer takes to actually process that at the network layer and send back an ACK. But yeah, empirically that will take a little bit of time and you would have to compensate for that. Yes?
It receives a NAC back. Does it preload the window, like stick that extra, pull one out and put in the datagram that didn't get there?
Yeah, if you get a NAC back, then you say, okay, I need to transmit another couple of data, however many are datagrams didn't make it through, and you send those over. And as you can imagine, that disrupts the flow, right? Because now you still have to wait for the permission to send. And the pipeline over here that was going it gets disrupted too.
The acknowledgement is just that it's been received, not that it's been processed.
That's right. That's right.
If you send it 100, it'll say, yeah, I got 100.
Yeah.
Drop 75.
Well, yeah, there could be errors in processing, or there could be some issues, but that's at a higher layer in the network. At this layer down here, where we're doing flow control, it's typically at the network or just the layer just above that. Like in the case of TCP/IP, it's just above the network layer. But in terms of the application layer, maybe those packets matter, maybe they don't at that time. So we don't know. We don't want to introduce any overhead that everyone's going to have to pay for. Yes.
In this model, it's implicitly assumed that the receiver has a buffer that will be at least 1 window size, or on the order of 1 window size. Is that a safe assumption to make generally? Generally,
you can assume that when a receiver asks for a certain window, that they have a reasonable buffer. Generally that's a pretty good assumption. The problem might happen is one problem that might happen is if the receiver, you're sitting there, imagine you're clicking on a bunch of different things, and all of a sudden all this data starts coming in. That could overflow the buffer. Another assumption here is that the processor can actually handle all that data. If you're running on a 486 and this is a 100 megabit per second line, there's an 8 megahertz bus in there that might prevent you from actually even get that data and process it. But those are all things that when you actually design these algorithms for practical use, you can't. In this case, we're assuming that this is 3 and it's always going to be 3. That's a huge assumption that you can't make. You're probably going to have to do some kind of timing and maybe say, okay, I'm measuring round trips and I'm going to take the average of the last 10 round trips and use that as my assumption for what this is going to be the next time. Things like that are going to, these practical implications have to come into play. but the main idea is still there. You have a window size, you have to wait for permission to send something back, and you want to pipeline it so that the bottleneck, which in this case is the receiver, isn't being overloaded, their buffer isn't being overloaded. Other questions about this?
The bottleneck is not necessarily the receiver. It could be somewhere along the line.
Absolutely. It could be something in here that is a slow link. And it used to be, for example,
Until after our first window fails.
yeah, or you might, sometimes you might time this. There might be information that you have where you've timed this route before, and you might try that for the first window. In fact, there's this startup that I was talking to some of you folks about that a few, maybe it was like 8 months ago. What they were doing was running around. They had all these different computers all around the internet, and they were actually timing, sending these packets back and forth to try to figure out what the congestion was, available bandwidth would be, latency would be at different times of the day, different times of the week, and they wanted to use that data to try to optimize flow through the internet on using some statistical modeling, and this for multimedia. So this is an important enough issue that there's actually, these are people from Bell Labs, like really about 11 of them, senior guys who actually think this is so important that they would be willing to go out and take a big risk. Any other questions about this? So naming is a big thing in systems. And what is naming? Well, naming is, the idea is that you have a namespace, a set of possible values. And naming is the idea of making associations between names and values. There's nothing that says you can't have two names referring to one value. But this is very generically, very high level what it is. Now let's get some terminology. Each one of these associations is called a binding. And the process of determining what value a name is bound to is called name resolution. Now this is very similar to what you've seen in Scheme. There's environments and so on. And in fact, even here there are what are called contexts, which is that a context is a set of bindings for a given namespace in a given set of values. So one context, for example, is domain names on the internet. You could have that same names. You could use that same namespace in your Scheme programs to come up with Scheme variables that correspond to Scheme objects. That's a different context. In Grapevine, you can have, you can do the same thing. You can have domain names associated with some kinds of addresses. That's in a different context. So when you think about name resolution, either explicitly or implicitly, there should always be a context that you're referring to. And in this case here, if this is the primary name for something, and this is a secondary one, we can call these all actually aliases for that name. And in Scheme, you can have aliases also, right? You can say define foo to be cons of something, define bar to be foo. Now bar and foo both point to the same structure. So what's a name service? Well, a name service is a service that helps you resolve names. And it may or may not be fully automated. So there's a few examples. One of them is the domain name service on the internet. And we're going to go through that in lecture for the second half of lecture. It's also part of the chapter that I'm asking you to read tonight from the book. But this is an important aspect of the internet, so I'd like you to understand how it works and what the issues are around it. Grapevine, you guys have all read about Grapevine. There's another, and they have all this great stuff around naming and how to manage consistency, things like that. Ethernet cards, I'll talk a little bit about how Ethernet cards are named. Main thing here is that, what do we want from a name service? Well, usually we want speed. Speed is huge. The reason speed is huge is because it can be the case that, like for example, when you're on the internet, anytime you have a domain name, you need to look up the IP address. So anytime you have to send a message, you need to know what that is. And if that step takes a long time compared to sending the message or the processing you're doing on it, then you're wasting a lot of time. Availability. If you can't resolve names on the internet, you're hosed, right? You type in http amazon.com and it just sits there and says, I don't know where to send this to. So it's a type of blocking operation. And scalability. You don't want to have a name service on the internet that only scales to thousands or hundreds of thousands. You want something that scales way beyond that and still gives you these other two objectives, which are speed and availability.
What about accuracy?
Accuracy, we're going to get into that. We're going to get into that because it isn't on here for a reason. So let's take one example, Ethernet cards. So how many of you all have ever picked up a raw Ethernet card and seen this number like this? It's a hexadecimal, and it's 6 sets of these 8-bit. What is that called? Do you guys know what it's called? What does the MAC stand for? Something like media address, something or other. But the point is that it corresponds to an address that corresponds to the media. Okay, and that media is either the card or is it can be a PCMCIA notebook card. And what that is, it's a unique 48-bit name that refers to that specific card. Now notice this isn't like an IP address. How many bits is your IP address? 32, so there's sort of 4 giga addresses. How many are there here? Many, many more. And one good reason why you want many, many, many more is that every Ethernet card has to have one of these. And when you think about it, how do you know when an Ethernet card is out of commission? Ethernet card is out of commission, or gets thrown away, or who knows? Who's gonna keep track of all that? So in a sense, what's going on here is that these addresses, once you issue one, that's it. It's taken. You can never be sure that it's ever going to be retired and reused. Now, why do we need these? Well, imagine at the very lowest layer when you put an Ethernet card on the network. I mean, it doesn't have an IP address at that point. That's at a higher layer. So there has to be some way of differentiating that card from other cards. So that on the network you can send messages to that host, to the host that's connected that is using that card. So this is why you need it. This is the lowest layer naming mechanism, and each network protocol at the link layer will have something that have a mechanism to recognize what these numbers are for Ethernet in this case. So how do we assign these? Well, manufacturers get these from a central naming authority. And this naming authority will say, here's your block, and you can go in 3Com, you can make a bunch of cards with this block. Lucent, you can make cards with this block, and so on. And when a manufacturer runs out of addresses, they come back to the naming authority, and the naming authority gives them another block. Now, you can imagine that this system does have some inefficiencies. You don't want to give a block that's too big to a manufacturer. Because once you give it to the manufacturer, I mean, what if they go out of business and and you don't know which ones they actually used and which ones they didn't? I mean, you're almost safer just once you give one of these out as a naming authority. You block the whole thing out and never try to recover them because you have no guarantee that the manufacturer has good enough operating procedures that if they tell you we didn't use these, they actually didn't use them. And so the big issue, of course, here is like what happens when we run out of names. Well, I don't know. I mean, how many names do we have to go through here? What is 48 bits? Well, it's
4 billion times 2 to the 16.
well, it's 8. So every 2 to the 10th is approximately it's 1 kilo.
4 gig.
What's that?
It's a lot. 256 terabits.
It's 8. So it's 8 bits is 256, and then 2 to the 40 will be it's 256 million because 2 to the 10 to the 4th, right, is a million. So it's 256 million, 256 tera cards. right? Which seems like a lot.
Are these only used for cards? You said there was something about PCMCI.
PCMCIA cards, also like your notebook.
Would they use the same naming scheme?
Yeah. The scary part is what happens when you start when you want to have Ethernet capability built into smaller and smaller components that are really cheap. Like you've heard about, nano type technology or very miniaturized technology. You've heard about technology that you can just throw away because it's so cheap, but you still want connected in some way. Then that's when you start, when this issue is probably going to start becoming more of an issue. Because what happens when everyone's buying, a cheapo thing that you throw away the next day, and then you buy one of these, the next week, and everyone's just going through them very quickly.
Well, they have expiration dates on them.
Yeah, so you'll have to do something. You'll have to alter the way that you manage this for that.
How many hamburgers has McDonald's sold?
80 billion?
About 80 to 100 billion, I thought.
Yeah, I think that's what they stopped counting after a while. Yeah, this number is very huge, so it's unlikely to. I mean, it's the problem that we have is that technology. Remember, we said exponentially increase. The technology curve exponentially increases. And so if the number of the types of gadgets or the size of things gets smaller and we start using more and that number exponentially increases, then we have to start worrying about this. If we don't have the exponential increase, then we probably have more time to spare.
The IP address is 128.
Those are IP addresses. So those addresses are network layer addresses, and these are link layer addresses. So these are ones that each Ethernet card doesn't have an IP address associated with it because it could be used for different types of networks besides the internet. It could be used for Microsoft, Novell. This is a lower level.
If you ever came close to running out, and especially if there was a specific class of technology that was causing it, couldn't you just update the protocol to say that one specific reserved name will have the meaning? Look for a second name because we've run out of space.
Yeah.
And that way you can just keep extending it.
You can do something like that. The one issue with that proposal is you have to implement it. It has to be backwards compatible.
Well, I mean, unless it was in something like nanobots where you can sort of create a special nanobot specification.
Yeah. Yeah. I mean, what probably will happen is once that technology comes up, and if they do want to use these MAC addresses, there's probably going to be a lot of discussion about how to make sure that those types of devices don't cause this namespace to run out. And it might be a completely different namespace, or like you said, something that's backwards compatible that sits on top of the existing one. But I don't know what that who knows what that's going to be until it actually happens.
Ethernet specifically, they don't all need to be unique, they all just need to be unique within their Ethernet network, right? So as long as it's big enough that there's a virtually zero probability that cards with the same name are going to be in the same.
Yeah, I mean, you can get into these arguments to figure out what's the probability. For example, you can say if I gave out a block of these, 10 years ago to someone, and these were the Ethernet cards that we were using coax cable, like the ones you read about, and these are 1 megabit per second or 3 megabit per second cards. You might argue that, well, I'm gonna assume that those are gone, long gone, and I'm just gonna start reissuing that block. So you can do things like that. The thing that you have to be careful of is, what happens if some of this technology makes its way around the world, to other places, and it's still being used there. And imagine you take your nifty new computer and you go to some other place, and all of a sudden there's this name clash and you can't get on and your presentation goes bust. I mean that you can get into arguments like that, which are probabilistic, and I'm sure there'll be discussions around that if that namespace seems to be running out.
Would it be possible to scan the net and get the ID cards that are used and then see which of those addresses, that block of addresses, is no longer available, or because they're no longer on the net?
Yeah, you can. Let me answer the first part of the question first, which is that you can actually go and query the MAC address of a Ethernet card. That doesn't mean that it will give you the right MAC address, because you can spoof MAC addresses, but you can go out and query them. It's also the case that a bunch of these cards will sit behind corporate firewalls that won't let you suck that information out. But how many of you guys have Media? Do you guys have Media One Roadrunner? Or have you guys? So you know that the way they assign their domain names is they actually use the MAC address. So it's and what at least in Boston, the Media the Roadrunner, what it does is it's cable modem. They marry the cable modem to the MAC address that you're using, and I don't know why they want to do that, but they do that so if you switch cards, if you upgrade from 10 to 100, then it's a big issue because you have to be calling customer support to change that.
They do it so you can't put a router, so you can't have the installer come with a network card in the machine, and then the installer leaves and you put a router in the machine instead, and route it because they want to charge you if you route to multiple people.
Yeah, but you can do that if you just pull that card out and put that same card into a router. That's what I did.
You can't go to CompUSA and buy, a router in a box.
Well, that's actually what you can. The current generation of these sharing boxes, these routers / internet sharing boxes, they actually allow you to spoof the MAC address. So a friend of mine has one, and you can click on there and say spoof the MAC address that this machine has over here, and then it just does it. So as you can imagine, a lot of attempts to prevent the next good thing are usually thwarted very quickly. It's the domain name service that the internet uses, and I'm going to get a little bit more in depth into it. So the namespace is a set of domain names, and you've seen them all: Amazon.com, mumble.mumble.mumble. They're usually some name 3 dot name 2 dot name 1. If you look at the at this N1, whatever's the last piece of it, that's usually called a top-level domain. Someone give me some examples of these. Com, net, gov. Man, there's so many. You guys heard of the one TV? Now there's some new ones that are proposed that are supposed to be coming out. What are those?
Biz professional.
Yeah, biz, name, web. What's that?
Ideal Lab just announced they're doing a bunch on their own.
Oh, they are on their own. Oh.
$25 per month. XXX.
Oh, really? They're doing XXX? Ideal Lab? Wow. What have they been doing with their money? Wow, I hadn't heard that. When did they announce that?
2 days ago, they sent the press release. But the thing is that you have to change the configuration of your computer to be able to see this one, and they have done like 25 of them, and they only charge you like $25 per year. And it's a bit controversial because they have this .xx or .kids, and they say, oh, we make sure the content is for all the kids. How do you do that?
Yeah. Well, yeah. Looks like they're grasping. Okay, so well, these names, what are they associated with? A number, which is which otherwise known as IP address. And what's the format of this IP address? Okay, and what's that something? 8 bits. 8 bits, 8 bits, 8 bits, 8 bits. For a total of 32 bits. Okay, so the whole idea is if you have one of these IP addresses, you can send a message somewhere on the internet. If you have a name, that doesn't get you anywhere anytime soon until you have this over here. Okay. So what do we need? Well, we saw some of the objectives before. We need scalability. We need speed. Well, how do we address some of these issues? Well, we're going to use our friend again, hierarchy, to reduce the complexity and to improve scalability. And we're going to use caching to improve our lookup speed and our availability. And just as a side note, DNS is typically implemented using UDP, which we talked about yesterday, rather than TCP. Can anyone venture to guess why you would want it as a UDP?
Yeah,
Lower overhead. TCP has all sorts of stuff that it guarantees, and DNS doesn't need it. So why hinder it with all that baggage? So the way this is done is DNS introduces this notion of zones. Well, a zone contains a bunch of different things. It contains, it's a table, and it can be represented as a table, and it contains specific information for some hosts in a domain. So there are different types. There are different types of information, and what's called record of type A is usually what? It's an IP address. There's several of these, but I picked some of the more common ones. MX is actually a mail exchanger. So we already know what an IP address, what that value is. For mail exchanger, what this usually is a pair, which is a host and a preference. So preference is some priority like 1, 2, 3, 4. And what this does is it tells you it helps you decide which mail host to try to deliver to the mail to first. You have records of type NS, which is name server. And you also have records of type CNAME, which are aliases. Now, name server and aliases, these can either be the values can either be a domain name or a piece of it, or an IP address. And the same for the alias. So what do these tables look like? Well, let's say we have the AD-UNI. Let's say we have a table for AD-UNI.org. They'll have something like, let's say that Shai had his own domain name on there. So it might say Shai, and this would be, say, a record of type A, and it might give an IP address for Shai's machine. So I don't know, 192.168.0.23. It's one thing that might be in there. There might be something that says there's another domain in here called, I don't know, Greg. Where's Greg? There we go. Okay. So let's say that Greg had his own little network on the side, and he had his own domain name server running over there. You could have something that says Greg, and then that's a name, and it's a name server. And I'll go through how these fit together. And let's just say we call that Greg DNS. And then we can have something that's called Greg DNS. And let's call that 192.168.0.51. Okay, so what do these tables mean in the broader context? Well, in DNS, I'm sorry, let me step back. One last thing that the zones have is some other information which we'll see later on around caching and replication. The way this works is you inject a query into the DNS. You inject a DNS query into the system. And what that does is, in general, there's a set of root servers, which are they serve top-level domains like aduni.org. They do things like yahoo.com. And there's a few of these root servers, and these are the critical servers that are spread around the internet. And though if you have to resolve a name all the way from the beginning, you start off here at one of these, and what this thing will tell you is where are the domain names, where are the DNS servers that handle each of these domains. So it'll say, well, here's one right here, which is sitting maybe in a box, in a local box. It might say, here's one for the star.yahoo.com. And notice that this one here says here's a domain name service over here for the star, or for the greg.aduni.org domain, subdomain. And it has its own table. So what you do is you go to the top. You say, okay, I'm looking for, let's say I'm looking for gambling.greg. So this is Greg's side thing here. greg.aduni.org. So what do I do? Well, I first look at this part here and I say, well, let's go to our root server and start figuring out how to resolve this. So root server says, oh, aduni.org, I don't manage that, someone else does. So we go to our aduni.org domain name server and we say we're looking for greg.aduni, or gambling.greg in here. So it looks through its table. It says, well, I don't know, I know that Greg is something I don't handle because I have a name server entry for it. And the person who does the Greg name service is called Greg DNS. Oh, you want Greg, and you can give that back. And now I say, oh, well, where's Greg DNS? Because that's the one I need to go to. So I go back through this whole thing, and I say, oh, Greg DNS. That's this. So now I have the Greg DNS IP address. So now I go to the Greg DNS server, which is right here, and it'll have an entry for gambling. And I'll type A, and it can have something like 10.0.0.7 to be lucky here.
Now, how does this relate to web addresses that are something gambling.greg.aduni.org / whatever?
That's a URL. So this is what DNS does is it just takes a domain name and it maps it to an IP address. Once you have that IP address, then you can start speaking HTTP, which understands what the rest of that URL means. But at this level, our goal is just to find this machine that's sitting out here somewhere. That's Greg's machine. That's this gambling.greg.aduni. Our goal is just to figure out how do we get messages to that machine to begin with. And so in general, you can see it's a little bit, it can take a lot of steps, right? You first, just to review, you first have to go and say, well, who handles aduni.org? And you can do that through the root level servers, which will tell you where that sits. So this is going to be, it's going to have some, A64.16.32.55, which is what this machine is.
So how do you contact to the first server? Who knows about that?
So the root servers are a set of well-known servers out there at the highest layer. But typically, when you actually join a network, there's two ways that you can hook into DNS that are common. One is you use what's called DHCP, which is a protocol that assigns you a DNS server automatically. And then the other one is where you actually just type it in by hand because someone gives it to you. Someone tells you, here's your DNS. So to get up here, actually, what you do is you go to your DNS server and you tell it, I want to know where this thing is. And your DNS server can come back and say, oh, well, I don't know where that thing is, but I can tell you where aduni.org is. And so then once you have the, it can tell you where the root server is. So once you have the root server IP address, then you can go query it directly, and go down like that. At some level, though, you have to know what the roots are, because it's great if you're on the fringe. Recursively, you can argue that anytime you add to a network, you'll always have a DNS server that you can contact. But at some level, you have to just know what the IP address is and type it in.
So you don't always start at the root necessarily. You start at your local place. It might pop you up to the root if you're not going down, and then you go down to the hierarchy.
Yeah, and we'll get to optimizations because I'm just going through this is the worst case.
What's the number of levels in the worst case? 3, 4 levels, right?
Yeah, typically I haven't seen domain names that have more than 5. So the more you put in there, the worse your performance can get. But when you first start, you can actually if you already have a DNS like through DHCP, then you'll probably start somewhere else to get to the root. if you might actually know the root address yourself and just type that into your computer, in which case you would automatically start up here.
So if you just open your AOL account or whatever, AOL will kind of set you up with all this stuff.
Yeah, AOL uses, I believe, DHCP. So they would assign you an IP address. They would assign you a DNS or a set of DNS servers, because usually you get 2, maybe more, and some other information about your subnet so that you can communicate. That tends to be if you type WinIP-CFG to any Windows machine, you get a list of information that has to do with your local network settings. But that's the kind of thing you get from DHCP. There isn't anything out there that's just an EDU level server. You think about why would that be? Well, let's say you wanted to get to, or a .com server, since I picked EDU. Let's say we said we wanted to find MIT.edu, and we just had a server that said, I'm the EDU server, right? Well, who's going to run the server that's, if I want to look for MIT.edu, right, then who's going to tell me where the MIT.edu DNS is? And versus the Cornell.edu, or is this? Well, it's probably going to be the same root level server, right? It's because you have there's all these if MIT runs its own thing, to get to the MIT one, you still need to go through the root. So the root ones will have these domain names of mumble.org, mumble.com, all the way down. The problem that happened was that as soon as everyone realized that these could be commercially interesting, they just went off and started buying them in bulk. And so there's a bunch of these that aren't necessarily even used, but just have been taken. Like what'll happen is when one of these top-level domains come out, people just go into a frenzy to buy anything that's 1, 2, or 3 letters. 1, 2, or 3 letters, because they're very easy to remember, and they're probably going to be useful to somebody. So those are usually the first things that are gone. And then the 4-letter ones and 5-letter ones, because there's more of them, they take a little longer to be gone. But usually, it's very hard to find any 4 or 5-letter names these days that are vaguely useful or memorable. Yes.
Clarify the difference between the zones and the domains.
Yeah, a domain name is something that a domain name is a name in the namespace, which is like mumble.mumble.mumble.mumble. A zone it corresponds to what a particular DNS server, what it manages. So in this case, a DNS server may manage a set of subdomains, which is pieces of that namespace, and it may manage and it may delegate, or it may have pointers to other subdomains. And so a subdomain is just a piece of that namespace, of the overall domain namespace. Other questions? Yes.
Because we use the word table, is that like the most generic word for there being some association?
Yes.
Between
Yes. Yes. And you can implement tables in a variety of ways, and you probably do. Like you probably want to have some hashing information or something to try to optimize the lookups. But in general, the association is a table, 1 to 1 to 1 in this case. Okay. So do you guys understand how this works? How this domain name service works, and how it can take a while to. One of the questions that I ask for tonight's assignment is around accuracy of this thing. So one thing to keep in mind is just you need to understand this to understand how we're going to optimize it and how that's going to introduce some issues. Okay. So this thing takes way too long, right? I mean, how many different messages you have to be sending back and forth to get something? Well, if you have to send 1 to your local because you're in DHCP, that takes you 1 to the root, right? Then that takes you back to something else, then that takes you back to something else. I mean, this is just way too many, and you're sitting there just sending these back and forth until you finally get this thing. In the best case, it's just 2 steps, because you go to your root, and then you get to the next place right away. The worst case, it can be a lot longer. The optimization is to use caching. I'm going to introduce the notion of 3 types of DNS servers. So there's authoritative, there's non-authoritative, and there's caching. Now, the authoritative servers are the ones that are supposed to have the most recent, up-to-date, like real copy of of these tables. And an authoritative, anytime you enter a domain into this whole system, it's required that you have at least 2 authoritative servers. And the reason for that is in case one fails, you want the other one to be up. And that when one fails, if both of them fail, then that's when you start relying on these other types of mechanisms. But you required at least 2. Some people have lots of authoritative servers because 2 might not be enough. And the non-authoritative servers, what they do is they replicate what the authoritative servers have. And the idea there is that they replicate it on a less frequent basis. So they do it maybe 1 or 2 times a day, or much less frequently, because remember, some of these tables can be huge. And so what assumption is underlying this? 1 to 2 times a day. Why so infrequent?
Updates are less frequent.
Yeah, that's right. You're assuming that updates are going to be a lot less frequent. So what ends up happening is that these non-authoritative servers then replicate the authoritative server data throughout the internet. And at the very end, you can have what are called, or anywhere in between, but usually at the very end, you can have what are called caching servers. Now, caching servers, what they do is whenever they get a DNS, whenever they perform a name resolution, they cache the results of that. So if they find out that gambling.greg.aduni.org is 10007, then puts it in a cache, in a table. And it just keeps caching and caching and caching. Now, the reason that's good is because if you're running one of these caching DNS servers on your local machine, is that now, instead of doing all this running around each time, you just, you ask for it and boom, it's there. It's local. You don't even have to go on the network. Okay. Now, before we get into the repercussions of that, one thing that a client has to be told is whether or not the data that it's getting is coming from an authoritative or non-authoritative source. So the client has, and this is to help the client decide what to do in case it's getting something that's consistent or not. So this issue was brought up before. There is no mechanism that guarantees consistency or DNS at all times. And one approach that people use to try to get this consistency, at least a little bit, is that there's this notion of a time to live number. What the DNS server can do is say, when it gives you a DNS, an IP address, is to say the time to live for this is a day or a week or something like that. And the caching server has to invalidate that entry once that time limit is done. So this is one thing. If you run a DNS service and you say, well, in my, like down here at the lowest layer, and say Greg is, he connects his computer and takes it off, once every hour so the feds don't find him, then his time to live might be something like, something shorter than a day, right? So it might be a little bit more frequently because he doesn't want to miss a single customer. But someone else, like Yahoo.com, might have it a little bit longer. For Akamai, it might be quite a bit shorter, because Akamai wants to be able to direct where you get your information from and change that more frequently. So there are reasons why you would or wouldn't want to have that TTL be long. So let's finish up by talking about some of the issues here. DNS changes can take hours or days to propagate. How many of you guys own your own domain name? Okay, good. So you know that when you make a change, you always get this message back saying, this will take 24 to 48 hours potentially to propagate. I found that sometimes it's very quick and sometimes it's not. But that doesn't mean anything, because I could be behind some, maybe I don't have that name in my cache, and maybe someone next door to me has it in their cache, and they'll see my old one for a while. So the TTL partially controls that, and as a client, you have to decide what to do. So if you go out and get an IP address, you can't be 100% sure that it's the right one. So this actually introduces the next issue, which is that DNS can be spoofed at some level, which is that when you get an IP address, you can't be absolutely positively sure that this IP address corresponds to the machine that you're actually trying to reach. someone could have gone in and put a rogue DNS server on a network that hands you the wrong thing. These DNS, the time to live might not have been set right, so you're getting wrong IP addresses. And what that means is this is why when you're doing something like HTTP and you're doing a credit card, you usually have a secure layer on top of that. And what that secure layer does is it authenticates that the host that you reach is actually the real host, because you can't be sure of that just because you got this IP address from the DNS. The last thing here is that simple errors can create disasters. And to think about that, let's consider what happens if someone comes in and takes aduni.org at one of these root level servers and accidentally changes it to point to something else, like this XXX thing, right? Or something bad, and doesn't even realize it, and they walk away. When they come back, what could have happened at that point? A lot of propagation, right? And so how long does it take to fix something like that? Typically to repropagate out? Well, it depends on the time to live. It depends on, right? So this thing could be around for days. So if you go in and you imagine if you did imagine a different type of error. Imagine if you somehow accidentally shifted all the entries down by one or up by one, or did I mean, it's going to cause chaos. And there was an incident that happened like this a while ago, where somebody messed up one of these tables, and like in that way, where it's more of a global type change, and this information just got propagated everywhere. It caused a huge mess. It was found very quickly by the person, but even so, it caused a huge mess for quite a while, because these time to lives can be long, can be hours or longer. One anecdote is that, from what I understand, these DNS servers, they used to be hosted by I don't know if they still are, but these root level ones used to be these machines in people's basements. And there were these people who were sort of the keepers of these. And the reason that was the case is because, remember, a long time ago, not everybody had internet access. But you still wanted to be able to have these DNS servers spread out throughout the internet. And so sometimes, someone from BBN who's here who helped develop the internet, their research lab was here by the LYT station. I mean, those guys, I'm sure they had some kind of more interesting internet service. If they had, some of them might have had some of these boxes in their basement. There's probably good reading on the internet about how that's working and some of these anecdotes. So I suggest you take a look at that if you want to take a breather.
So who pays for these DNS servers?
What's that?
Who pays for it?
Well, at the root level, it used to be the case that these people who were the original founders of the internet were paying for it. So research labs like BBN and MIT and so on. These days, Akamai has a huge amount of these DNS servers all over the place for Akamizing content. Any of the major ISPs, Sprint, MCI, will have tons of DNS servers around to improve the internet access performance of all of their users. Media One, those guys. I'm sure the government has a bunch for all their .gov domains. So the cost has been distributed to the people who are funding, who either use the network like an ISPs, or who fund it, or also companies internally inside companies. They'll have a DNS infrastructure, because if you're behind a firewall and you have your own sort of IP network behind it, you'll want to also have a good performance. Other questions about this? Okie doke.